Okay, good afternoon. Let me ask if you have any questions before we continue with our discussion about time-independent perturbation theory, okay, which we saw last time in we did the outline of the general case for at least for a non-degenerate spectrum, and we did as an example the harmonic oscillator with a linear potential. So in the presence, say, of an electric field and the charge. Okay, this we saw that can be solved exactly by a shifted Gaussian, and you can calculate the correction to the energies, which come purely quadratic in the field. So the second order perturbation for the energy is exact. Not exact for the state, however, which you can calculate to say, first order and see what it comes with respect to the actual one. Okay, so if you have no questions, I would continue and do a second exercise. This will be mostly a series of exercises, really. But I hope that you get a feeling of what is the, you try to do things yourself, okay? Not so these are less kind of theory-oriented lectures, more on the practical side, okay? So for instance, suppose that your Hamiltonian now is, again, the harmonic oscillator. So p squared over 2m plus 1/2 m omega square x square in one dimension, for instance. And now you add the term. So this is a potential like this. We added the linear term. The linear term shifted the parabola, right? What is the next term you can add? Not a quadratic one, because this would change simply the frequency. So next, constant is not important. What? Cubic. Cubic or quartic? What do you prefer? Cubic. Both are important and slightly different in some sense. Let's first discuss. You have to decide this for the quartic term, okay? So something like plus gx to the fourth. You have to decide the sign. If you decide a positive sign, then this means that the potential really is much more steeper, especially for large x. If the sign is negative, however, there comes a problem. If the sign is negative, x to the fourth eventually wins, okay? So immediately understand that positive or negative is tremendously different, okay? Whenever this happens, you should not expect that the problem is perturbative in G, in some sense, okay? Because you see that it's not so much the fact of G being small, but the fact that G positive and G negative, no matter how small it is tremendously different. In particular, for G positive, you expect just a small shift upwards of the energy level, but the ground state will be somewhere here. For negative G, on the contrary, you see that the potential does not confine any longer the particle. The particle can escape, and in fact, the ground state is now down to minus infinity. There's no ground state. So whenever this is the case, the perturbation is in some way singular, so you do not expect that any power series you write to give you a convergent expansion. Forget about convergent expansions. At best, you can obtain asymptotic series, which are a strange series, okay, which for a while you keep increasing. If the amount of the perturbation is small, for a while you increase the order of the perturbation and you improve. But if you insist, then the thing really diverges. Okay? So asymptotic series are really divergent series, which, however, improve systematically for a while on the quality of the perturbation or of the approximation if the amplitude of the perturbation is small. I don't really discuss this in any way. I don't want to touch it. It's just a warning. Don't think that our perturbation series is always a convergent series. Okay? So if I include second, third, fourth, I would do an exact job. Okay? There are problems which have intrinsically no convergent series behind. Okay? And usually you can spot those problems by the fact that positive and negative value of the coupling have a completely different physics, for instance. That is a signal that should tell you don't trust don't think that there is a convergent expression. Okay? So we could do this. Okay? It's just a little bit more complicated because of a thing that you will find immediately now than doing the third order term, which I will write for simplicity in this way. I will write it as minus lambda. I want lambda to be dimensionless, just to gauge the amplitude of the thing. Then obviously I will need an energy. Let me write this energy as h bar omega. I want x to the cube, okay? But since I put all the dimensions here, I write this as x divided by the famous L, the oscillator length. That is some function of h bar, m, and omega, okay? In this way, this is dimensionless. This is the energy, and this is another dimensionless quantity, which is essentially how big is the perturbation. What? Cosine of x? Well, that is a very different thing, first of all. Cosine of x behaves in a periodic way, okay? So that changes, in some sense. First of all, notice that this object here, once again, has the following thing. For negative x, this goes to, if lambda is positive, for instance, this goes to a very large quantity like this. But for positive x, this, in the end, wins over this. So you will have something like this. Okay? So this potential also has that feature that really there are no ground states to be expected. Okay? So as before, you expect that this thing should not be particularly nice as a function of lambda. It's not convergent in lambda. We will see several signals of these delicacies in lambda. Then you might ask, then what for? Why do you do it? Okay? Well, if lambda is very small, and we will see to characterize what does it mean to be small, then what used to be, for instance, the ground state here, the ground state of the harmonic oscillator, in some sense will keep a certain validity in the sense that this will be a kind of metastable state of this system, which means that it is a long-lived object. If you prepare your particle there, it will stay there for a very, very long time. And you can make this time longer and longer if you make lambda smaller and smaller. Okay? So in some sense, it is reasonable to think of them, of these objects, although, strictly speaking, there are no exact states of the Hamiltonian. They are only metastable states. So they will eventually decay, and decay by tunneling through this barrier and go to plus infinity. Okay? People might sometimes rephrase this thing by saying these states have a small imaginary part, okay, in some sense. But we are not concerned about this, okay? Particle physicists are particularly sensitive to these things because, after all, many of the things that you call particles are really bound states that have a certain decay time. They decay after a while. They are metastable objects, okay? They just split into other things. So in some sense, this is very common in particle physics, okay? So there are objects that live for a certain time and then they split, okay? Less common is obviously in condensed matter, but nevertheless, this is a possible scenario, and it is reasonable in some sense to still consider, especially if you have here this object. I mean, if lambda is very, very small, then this thing will go up, 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 and then eventually, okay, will go down. So maybe there are quite a few levels of the harmonic oscillator inside the well, which would retain some interest as metastable state, obviously. And you can ask how they change in mean energy, obviously, okay, together with the fact that sooner or later they will decay, but they move in some sense. You can ask in the meantime where they live, you can try to address them by exciting things, okay? So for instance, you can think of what photon we would need to excite one of these metastable state to another. So the energy difference between them that you might try to calculate, that we will calculate, have a certain meaning, okay? Although strictly speaking, neither of them lives forever, okay? This is a clear thing? Okay. So let us try to calculate this because it's slightly simpler. You realize why. X over L is what in terms of creation and annihilation operator? We said we make the position dimensionless in such a way that we essentially express immediately it as A plus A dagger over square root of 2. It's good to get rid of the dimensions. Otherwise, A and A dagger have all H bars, M, and things appearing in a very ugly way. Okay? In this way, things are simple. All right. Now, you see, you have to take the cube of this. For the other problem, x to the fourth, you have to take the fourth power. So the algebra is slightly heavier. Okay? We get 1 power less, okay? And this is slightly more, slightly easier. Okay, so what do? Well, we simply rewrite this object now in terms of A and A dagger, okay? So this is my perturbation V, or lambda V, okay? Lambda V is what I write there. I want to rewrite it in terms of creation and annihilation operator, and then you remember that all I have to calculate is matrix elements of this V between the unperturbed states, which are the well-famous states with a certain number of occupation of A daggers, the psi n, okay? So the phi 0 n, let me write it here, phi 0 n are simply A dagger to the power n over square root of n factorial applied to the vacuum, okay? The thing without objects, okay? And these have energies E0n, which are simply h bar omega n plus 1/2, okay? This is the unperturbed part, okay? After obviously getting rid of the... Okay. Good. So let us proceed. I calculate this. So I have this object to be just minus lambda h bar omega. Then I have what? Then I have this thing to the cube. So I have A plus A dagger cubed. And then I have the 2 square root of 2 because of the cube of square root of 2. All right? So let us calculate this thing. You have to be a little careful because these are operators. They do not commute, so don't just use the cube of the binomial as you would do. The result is the following. Let me first write it, then we comment on how to get it, really. The result is the following. A cube plus A dagger cubed, and this is very reasonable, right? I mean, after all, you have the best thing is to just directly see all the terms by just calculating the product. So A gives you A cube, A dagger gives you A dagger cube. Then normally you would write plus 3A square in classical, for a classical binomial would be this plus 3 a dagger square, right? Now you have to be more careful. This is not right. If you do it correctly, you get, first of all, you see that hiding behind this thing, there is the operator n, a dagger n. Okay, this is an operator that counts n. So n applied to phi 0 n simply gives me the number n times phi 0 n. Okay, it counts how many times a dagger appear in the state. Okay, so this is hiding here. You see a dagger a is there, a dagger a is there. It's simply sitting, in an arbitrary position if I write this way. So we have to account for it correctly. The result is the following: plus 3n a dagger plus 3n plus 1 a. Okay? Let us try to see why this is so. Okay? So, counting 2 times 2 times 2, 8 terms. Okay? 1, 2, 6 more. Okay? So, let's see. The 6 more terms will be, for instance, let us be systematic. 1a and 2a daggers can appear like this. Okay? Or the a in the middle. Or the a at the end. Okay? This is the terms with 1a and 2a daggers. And then I can have the opposite, 1a dagger and 2a. And this can happen again with the a dagger in front and the 2a after, or the a dagger in the middle and the 2a here, or the a dagger at the end and the 2a there. Okay? Now, let us try to recognize the n. You see, this is, for instance, a term like n times a, the operator n times a. This is a times n. This is nothing. This I should first commute it in order to get some n there. Let us see here. The same here. This is, on the contrary, n a dagger. This is a dagger n. Okay? And here I should first move a dagger in order to get n involved. Now, you should track all these 6 things, and in particular, notice the following thing. If you have a n, then it's simple to calculate, obviously, but also to just argue that if you first count and then distract, it's the same thing as first distract and then count, but adding 1, okay? Because after all, with respect, this will give you 1 less, because after all, A already has killed 1 of the present. Okay? You can verify it with the commutation. Okay? It's very, very simple. If you are suspicious, just do it. You will see that there is an extra 1 coming from the commutator, and this is the result. Another result that is possibly useful is the following. A dagger n, if you first count and then you create, it's equivalent to first creating and then counting, but obviously subtracting 1, because there's 1 more that you have just created that you shouldn't count. Okay? So these 2 things you can verify, and they are useful because you immediately see that, for instance, something like this can be written now as, with the a to the right, as n plus 1 a. All right? And you can use several times this trick in order to have all the a's, for instance, or a daggers to the right, and all the n's to the left, okay? Which is very comfortable in some sense, because you know how A and A dagger act, and then you count the remaining. All right? So if you do this thing, the 6 terms all reduce to either one of this, either n A dagger or n A or n plus 1 A. Okay? This is just a matter of wasting a few minutes in calculating the possible commutators and things. I don't think that there is very deep physics behind. Okay, so I would just give you the result there. Try to verify from the 6 terms. All right. Now you realize why I didn't do the quartic term. Okay, the quartic term would imply a further A plus A dagger, which means twice as much terms, which you should rewrite and re-express. It takes a little bit more, but you can do it. All right. This shows already clearly what you have to do in the most general case. Okay, so let us calculate now the necessary ingredient. The ingredient we need is the following. We have to calculate. Oh, first of all, first order and second order corrections to the energy. In first order correction, if you remember, the first order correction to the energy of a state n involves the matrix element of the perturbation on the unperturbed state n. Remember the formula? Now immediately see that the perturbation never leaves the state untouched, because it creates or destroys 3 particles or 1 particle, okay? And therefore, the result is never n again. It's something different from n, okay? So this immediately shows that the first order perturbation is 0. No correction to first order in lambda. So we have to go to second order, okay? Now I write the second order formula. The second order, if you remember, is minus sum over all m different from n of the matrix element phi 0 m v phi 0 n modulo square divided by E0 minus E0. Now there is m and n. Let me first put and then we check. Okay, I remember that with this minus sign, the ground state always goes down. For instance, if this is the ground state, all the m are greater than n, so this is positive, so they go down. Okay? So this is my mnemonic way to check that the m and n here are correctly. Sometimes you find it written with a plus and n and m inverted. The same thing, okay? But this is easy for me to remember, okay? Good. So this is the formula now. Now you see clearly that now the matrix element that I have to calculate are those with m different from n, which are indeed those that appear here, okay? So let us see. For instance, if I calculate, yeah. The question is why the first order correction is 0. Okay. Now, V, the perturbation here, acting on phi 0 n, can do essentially 4 things. You can destroy 3 A's, okay? Obviously, the result will be essentially n minus 3, right? So when I take the scalar product with n, I get 0. You agree with this? So this will give me 0. Same thing happens for A dagger cube. Because it creates 3 particles, it means I go to n plus 3 with certain matrix element that we will take care now, obviously. But the result is that you go to n plus 3. Then you take the scalar product with n, you get 0. They are orthogonal, all right? So even this is 0. Let's take that. That will be A dagger and then 3n. So I first create 1, and I get essentially n plus 1. Then I measure, which simply counts, so I get n plus 1 here. I multiply by 3. But the net thing is a state that is n plus 1. Then I take scalar product with n, I get 0. Okay? So everything here, including the last one, changes n into something else, either n plus 1, minus 1, plus 3, or minus 3. Never 0. Okay? Never 0 change. Okay? And therefore, when you take the scalar product with phi 0 n, you get always 0. Okay? This happens quite often. Okay? The perturbation is such that has no effect on the unperturbed state. The matrix element is trivial 0 by some parity rule or whatever. Indeed, I mean, in some sense, let us look at this thing from a different perspective. After all, this is x cubed, so it's odd. You take the matrix element between n and n. Whatever n is, it is same parity, so the modulus square times n. By the same reasoning we did last time, the result is 0 by parity. Okay? So this is a different way of seeing it, but more deeply. I mean, what is behind this thing is the fact that this is an odd potential term. So for instance, you realize that an even potential term, so something with the power 4, for instance, would have a contribution in principle. At least you should search for a possible contribution. Okay. Good. So let us calculate. V phi 0n. Well, it can go up to n plus 3. Okay? So let me calculate this one. N plus 3. How much it is? The only contribution to this matrix element comes from this object. Nothing else. Right? So this one will be minus, lambda for me now is really in the potential. So let me put it lambda. Minus lambda h bar omega divided by 2 square root of 2. And then I have, well, I first write it. Okay? Phi 0 n, a dagger cube, phi 0 n plus 3. Now let us calculate this carefully. The first a dagger, okay, will give me what? Will give me square root of n plus 1 times phi n plus 1. Then I have another a dagger and another a dagger because there are 3 of them. Okay? So the second one will give me a square root of n plus 2 times the square root of n plus 1, and then I get n plus 2. And the final one will give me, finally, square root of n plus 3 times square root of n plus 2 times square root of n plus 1 and phi 0 n plus 3. Is this clear? Okay? This is simply application of a dagger 3 times to n plus 3. To n. Okay? So as promised, I get n plus 3 with this peculiar square root. Now I take the scalar product with this, and all it remains is the square root. Okay? So I can just rewrite this as the square root of n plus 3, n plus 2, n plus 1. Okay? This is the matrix element, one of the matrix elements that will appear in the sum. Let's see if we can fish out the other. For instance, there will be the matrix element with n minus 3. Who is responsible for that? You immediately see, is this. Okay? So what is the coefficient? Well, the thing in front is the same, but now it's a rather than a dagger. So we'll get other square root, but do you remember which one? So the first square root is, for instance, I'll do only the first. A phi 0 n gives me square root of n, phi n minus 1. Okay? Then the next will give you an n, so I get n minus 1, n minus 2. Okay? This is fine. Now, let us do this two. So, I create one and then I measure. So I will get a matrix element between phi 0 n and phi 0 n plus 1. Right? Now, by creating one, I get, so the matrix element here is the same. Let's see if we are efficient now in calculating. If I create one, I get square root n plus 1. Very good. Then I measure. I measure now a state that is n plus 1. Therefore, the result of this thing is n plus 1, not n. And then I have a factor 3 because of this. Okay? So this is the result. Minus 3. Okay. Which you can write also as square root, if you want, of n cubed. It's the same thing. And finally, I have the other one, phi 0 n minus 1, phi 0 n. This time due to this term. Okay, this first destroys, so gets n minus 1. Then this counts. And then I multiply by 3. So minus lambda h bar over 2 square root of 2. You first destroy, you get a square root of n. Then you get n minus 1. You count n plus 1 of an n minus 1. Remember, this, not to confuse you, this is doing this. Okay? So it's counting, but then you have to add 1 on an n minus 1 state. So the result is n times n minus 1. Okay? So it's n, really, like that. Pretty much the same. So you get square root of n cubed, if you want. Now you have the 3. Okay, that's it. These are the 4 matrix elements that will enter this. No other m enters. You realize m plus 5 doesn't enter. Okay? Only plus 3, plus 1, minus 1, and minus 3, due to the structure of the perturbation. All right? Okay, so now you can put all the ingredients there. The denominators are simple. Okay? E0 n plus 3 minus E0 n is simply equal to 3 h bar omega. Okay? Because this thing differs by just a certain multiple of h bar omega, and the multiple in that case is 3. Okay? So you do this calculation, and it's rather boring. Okay? This factor is everywhere. Here you have many square roots, which you have to keep and do track, some factors, okay, and some denominators that could be 3h bar omega, minus 3h bar omega, plus h bar omega, or minus h bar omega, depending on which state you are considering, okay? Can I just give this to you to sort out as a private exercise in the afternoon or so? It's quite boring and perhaps not particularly illuminating. I mean, it's just doing careful algebra, which can be done. Okay, so once you do the careful algebra, you will have the following result. En, okay, up to the level of perturbation we are doing is the unperturbed one, okay, what we have. So this would be, let me write it explicitly, h bar omega n plus 1/2. No first order correction. And then you have a second order correction. Notice, if you calculate this, it comes in all cases negative. There are two actually pieces that you can extract. Minus 15 over 4 lambda square h bar omega Oh, lambda square comes because this matrix element have to be squared. Okay, so all the square root, in fact, disappears. Okay, because of the square. The lambda square, the h bar omega is not square because there are h bar omegas in the denominator that cancel partially this. So you see, you have only one. One term is this. And the other term is just independent of n, minus 7 over 16 lambda square h bar omega. Okay? So both of them have lambda square h bar omega, but this term has n plus 1/2 squared, and this term doesn't depend on n. Okay? So you see immediately a couple of things. First of all, given n, the perturbation tends to actually lower a little bit the energy, okay? From the unperturbed one, it lowers it a little bit, all of them. In particular, it lowers more as you increase. Let us see. Suppose that I calculate the energy difference between the level n and the level n plus 1, okay? Or n minus 1. So I do En minus En minus 1. Okay? So obviously, for the harmonic oscillator, would be just h bar omega. But now, this term, okay, this cancels exactly because it's the same correction in the two terms. But this doesn't count. If you calculate, you get the following. You get minus h bar omega, 15 over 2 lambda square n. Okay? Yeah.
I think I'm really confused because I saw that like just counting of the order of perturbation, but here it's there explicit.
Okay. Usually I use it only to count the order of perturbation. In this case, I mean, this has to be an energy, okay? So I prefer to explicitly insert the, here is really doing the purpose of telling me how strong is this potential, in dimensionless way, however, okay? So you can tell me this potential is 0.1, or 0.9, or 2, or 3, in units of what? Of h bar omega, which is the energy in front, and 1 over L cubed, which is in the denominator. You see that everything else is dimensionless. This is dimensionless. This has dimension of energy. So in some sense, this is now serving a more definite role. It should tell me how big is this perturbation. All right? So I leave it there. Okay? In our theory before, it was just a kind of signal of the order. Because I didn't specify the V in my previous lecture. I mean, V might have included the how. Okay? That was just a formal tool. Now, probably I should use another symbol. Would you like epsilon more? Okay? So, forget about the lambda of the previous lecture, keeping track of the thing. Now, I need a parameter telling me how big is this perturbation in absolute terms, okay? In dimensionless terms, okay? Because I have chosen, if I write this as minus ax cubed, everything is hidden here, obviously. But I know that this must be an energy divided by a length cube, because the result has to be an energy, okay? So I fish out the energy, I fish out the length cube, and the remaining thing is some constant, which could be small, large, whatever, okay? So this constant is lambda, or epsilon, okay? Perhaps epsilon is a better name. But let me not substitute everywhere, okay? So wherever you see lambda, call it epsilon. It's some number. Now, it is not difficult, this calculation that I am hinting. It's just the difference between two following one. So one is this, and the other is, you see this term has minus 15 over 4 epsilon square, or lambda square, h bar omega n minus 1/2, because if you decrease n by 1, you get n minus 1/2 square. So you take the difference of this and that, okay? And what you get is simply lambda square n. You realize this? It's very simple, right? Because the square of this is n squared plus 1/4 plus n, the double product. The square of this is n squared plus 1/4 minus n, okay? So if you take the difference of this and that, the n squared goes, the 1/4 goes, n minus n gives me 2n, okay? So you see here the factor has become from 4, 2, and there is an n, all right? So the gap between, so every level is just decreased. But the gap also between a level n and the level n minus 1 is decreased, and in fact, proportionally to n. So the more you go up, the more you decrease this gap. Now, how long do you think we can go up before this will make no sense at all? It's very simple to see that if you fix lambda and you take n large enough, lambda square n times 15/2 will become 1, okay? No matter how small is lambda, you keep increasing n, and this will become 1. At that point, this gap becomes 0 or negative, which is meaningless, obviously, because this should always be a positive number, okay? So you immediately see signals of something that is fishy, something that is obviously not right for all possible state, or certainly one has to be careful. I mean, the perturbation being small, you can believe those formulas for small n. Sooner or later, even if lambda is small, n is so large that you should not believe the formulas, okay? Because in some sense, the perturbation is not only controlled by lambda, but is controlled also by what is the n that you are perturbing. You see that the amount of correction increases with n. And at a certain time, it becomes meaningless. You are essentially correcting the unperturbed gap, for instance, by a quantity that is of the order of the gap. You should never believe to corrections that are of the order of the things you are correcting. Because obviously, maybe there is some further correction that changes completely the picture. And in any case, this is a signal of a series that is not convergent in this case. Okay? Nevertheless, if lambda is small, so this is very, very large, here there are several levels there. For some of this, especially the lowest one, you can calculate how they shift. Okay? They shift a little bit down. So you calculate how the photon resonances, for instance, would change, and perhaps these are experimentally meaningful things that you can try to control. Okay? Strictly speaking, no single level there will survive. Sooner or later, this will go. But it's a metastable state that lives for long enough that you can possibly measure things. All right? Okay. So hopefully the calculation is clear. You go and look for the perturbation. You check if there are diagonal matrix elements, because this will give you a first order correction. If they're not, you proceed to second order. Second order, you have to look for all matrix elements that give you a contribution, or of diagonal. You have to obviously be able to calculate the denominator and the matrix element squared in the numerator, and do the algebra neatly. Okay? That's the recipe. Yeah. Really depends. Depends on what people ask you. If they ask you calculate up to second order, you do the first and you do the second. The idea is obviously that you always have to check what the parameters are. If the second is smaller than the first, for instance, that is a good sign. It means the perturbation was small, and indeed the second correction is smaller than the first. If the second is larger than the first, already be suspicious. The third might be larger than the second. And so you really have to check. I mean, you want to stop in a perturbation expansion in some sense when the next term you forget is smaller than the previous one. This is roughly the idea. Obviously, If you can do up to second order and it would take 3 years to calculate the next order, then forget it. This is what you can do, and this is the result to the best of your capabilities, okay? But in general, if you have some way of gauging different terms, that helps, okay? So if there is first and second, you can realize if with the parameters you have, if the second is smaller than the first, okay? That is a good sign. Sometimes the first is 0, okay? So there is no way of the first non-zero term is the second. So consistently with what I've told you, in principle, you should tell me if the third is smaller than the second. You never do that, but at least you try to calculate if the second gives a small correction with respect to the unperturbed gaps, for instance, okay? So by adding second order correction, how do the gaps change? If they change a little bit, then it's reasonable. If they change completely, for instance here, they would even reverse sign at a certain time. This is completely unphysical, okay? You realize that this cannot happen, and therefore you realize that you shouldn't trust this thing if lambda square n times 15 over 2 is of order 1. Yeah. No, I didn't say that. I didn't say that in general the first order correction is 0. Sometimes it's 0. Eh? You go on. I mean, it's easier to calculate something that is 0. You look at it, it's 0 by some better. Usually it's 0 by some symmetry. Okay? For instance, the states are even or both odd, and the operator is odd under parity. Okay? Let me give you this once and for all, because I promised that sooner or later I would give you this little selection rule. Okay? So let me give it to you now. You remember, if parity is a good symmetry, so the inversion commutes with the Hamiltonian, for instance, the potential that you have is symmetric. It means that the parity commutes with the Hamiltonian. You can classify all the energies, all the eigenstates, as eigenstates of parity as well. Okay? So you can always take simultaneous eigenvector of parity and Hamiltonian, which means that every eigenstate, you can tell me if it is even or odd. Okay, now, suppose that I have some state, okay, phi n, okay, which has a certain parity. Say the parity can be plus or minus. So let me say that this is -1 to the parity of the state n. The parity for me is, for instance, 0 if you want to have a plus parity, and 1 if you want an odd, because -1 to the 0 is +1, -1 to the 1 is -1. All right? So this little number here will tell me if the state phi n is even or odd. All right? Good. Now I have some operator, and now I have another state. Okay? The other state also has a certain parity. So for instance, -1 to the pm. Again, if pm is 0, you mean even state. If pm is 1, you mean odd state. Okay? Good. So how can I tell you something about this? Well, first of all, I can insert here P is the parity for me, okay? P dagger, okay, is obviously an identity because we said all the symmetries are unitary operators. And so the inverse and the dagger coincide. By the way, in the case of parity, the inverse coincides with the parity itself, okay? So operating the parity once and then twice gives me the identity, okay? So I might as well use another parity here, but never mind. What I do is I insert a parity here, and then I insert a parity here, because this is identity. So I have on this side, I will write it like this. P dagger P. Okay? Now, you immediately see that what you have here is equal to the parity applied really to this, to that thing, to the left. Then the parity V and parity again in the middle, and then P applied to phi n. Okay? I have simply reassembled things to show you that here you have a parity operator acting on the state, and this is an eigenstate. Here you have a parity operator acting on the eigenstate to the left. Okay? So these two objects, this will give me -1 to the Pm times the same state. This will give me -1 to the Pn times the same state. And now the crucial question is, what about this? Okay? So you immediately see that this object is essentially how the operator behaves under parity. You first change parity, then you measure the operator, and then you revert back. Now, if the operator is, for instance, even, it means that this is equal to V. If it is odd, it means that this is equal to -V. Okay? There are two possibilities. The operator is even or odd. For instance, x cubed would be odd. So if you first do the parity, then you measure x cubed, and then you get -V. All right? X to the fourth would be even. Any operator, in principle, you can try to classify if it is even or odd. If it is mixed, then obviously it must be a sum of even and odd. You can address the two parts separately, okay? But in principle, you can do this analysis. Now, look at this thing. Suppose that you have an even parity object, okay? Then this thing will be equal to what? -1 to the Pn plus Pm times phi m v phi n. Okay? So quite the same object appears there and there. Okay? But the thing in front could be +1 if the two states have the same parity, or -1 if they have opposite parity. Well, if they have opposite parity, a number cannot be equal to minus itself unless it's 0. Okay? So you immediately conclude that the number must be 0 without calculating anything. Okay? Notice, if I had x over L to the power 17, before I end up doing my algebra for the power 17, I mean, it's the end of the day, I have to go for dinner, and I still don't know if my first order thing will be 0 or not. It is 0 by this argument, okay? All right? You don't need to do all the algebra to conclude that the result should be 0. The opposite case of an odd parity thing is very similar. You get an extra minus sign in front, okay? Which means that this time, if the parity of the two things is opposite, there is a minus from here which cancels the minus from there, and then you have a possible non-negligible, non-vanishing matrix element. Otherwise, you should have 0. Okay? So same parity states will have a 0, like here. All right? So this is a more general object that allows to conclude on other things. For instance, sometimes you need to calculate the matrix element of momentum operators between atomic states, like hydrogen states, which have a definite parity. If you remember, the states of the hydrogen are radial functions times spherical harmonics. Now, the radial functions obviously are just even, but the spherical harmonics, they can be even if L is even, like 0 to. If you draw the D functions, you must have noticed that the lobe have the same sign, plus plus, minus minus, things like this. On the contrary, the p states, L equal 1, have opposite sign, plus, minus. And this is a general thing. Odd spherical harmonics are odd, and even spherical harmonics are even under parity. So immediately you can conclude, without even calculating the gradient, that the average momentum between, say, same L spherical harmonics should be 0. Because same L or same parity. Because P is odd under parity, and the two states are even. Or even if they are odd and odd. I mean, the two oddness sum together to give you a. All right? So this is selection rules into play. And there are other selection rules that you can use by, rather than applying parity, applying angular momentum. These are slightly more complicated. Probably we will mention them later on if needed. All right. Is this clear until now? Okay. Now I want to do with you the final exercise of non-degenerate perturbation theory, which I think is very, oh, yes, exercise for you, together with doing the algebra of all this, the cube and this final algebra exercise for you. You remember that you can calculate not only the second order correction to the energy, but you can calculate the first order correction to the energy by just using the same ingredient, okay? So the state is perturbed with essentially a sum of over m different from n of these objects divided by this, okay? Now I can ask you, what is the average? Suppose that you take the ground state of the harmonic oscillator, phi 0, 0. You perturb it, okay? So you will now have some phi 0 up to first order. So this is phi 0, 0 plus some corrections, okay? So something like minus sum over m different from 0 of these objects. Okay? Divided by E0m minus E00 times phi 0m. Things like this, okay? If you want the formula with all correct signs, I will give it to you immediately. So it is this. The sign, well, it is like that. So this is phi 0m, this is phi 0n, the v phi 0m. Okay, and if I write it like this, there is a minus. If I exchange, there is a plus. You can decide. Okay? So now, obviously, if I start from 0, this is 0. This will not go to negative. Okay? So you will have only this and this. Okay? The negative ones will just not contribute. You see immediately, you get square root of 0, square root of zeros, okay? So no negative, only the positive. There are two contributions, however. So the ground state is perturbed by the state with +1 and the state with +3. So you have a precise wave function, and you can calculate what is the average x on this new wave function, okay? On the previous wave function, so if I calculate this, you can tell me immediately how much is this. For the unperturbed harmonic oscillator, the average x is 0. Same argument as before, even, odd. All right? But now, on the perturbed state, the argument fails. The perturbed state, you see, is an odd state, the Gaussian, plus things that have +1 and +3, which are odd. Okay? So it's neither odd nor even. It's a mixture of things. And you can calculate what is the average x for that thing, and you immediately see this shifts this up, and there is down. So what do you think will do the particle on average? Can you see the movement of the particle? The particle will have an average which will be now positive, because it is pushed from the back and helped with a very nice negative energy on the right. Okay? So the average thing becomes now, it becomes the following. I missed it. Becomes 3 lambda L divided by 2. Well, L you might have guessed is the only length in the problem. Lambda you might have guessed is the perturbation. The 3 over 2 is the only thing that you need to calculate. Okay? So out of all this matrix element and things, when you calculate the matrix element that you need in the end, you get a 3 over 2. All right? So a positive energy on. Okay? So it's like if this cubic potential tends to suggest to the particle to be more positive than to the 0. All right. Okay, let me just try to do, if I can today, the van der Waals attraction between two hydrogen atoms. There are questions on this? No. At least the setting up of this problem. I don't know if I will be able to finish the calculations today. I wanted to, but I wasted too much time. Okay. I want to do this exercise with, kind in detail, because it's very physical and it teaches you a few things. So the problem is the following. I have an hydrogen atom here, okay? I schematize it like this, a proton, and the electron running by. And then at a certain distance far away, r, I have another hydrogen atom, okay? So this is hydrogen and this is hydrogen. And I ask you, what is the interaction energy that these two faraway atoms will feel? On naive arguments, you might say this is neutral, so therefore there is no charge, they will not feel any attraction. That's it, 0 potential. The answer is no. They indeed feel an attraction, okay? The attraction is, we will calculate today, minus some constant divided by r to the 6th, the distance between the two atoms to the 6th power, and is negative. Obviously, this will not go forever, so don't think that this will just diverge like that. On the contrary, when these two atoms come closer and closer, other terms will keep, will be more and more important, until if you really try to squeeze one atom on top of the other, the nuclei would repel like hell. The two electrons also would come close to each other, would repel like hell. So really, here, there is a strong repulsion, okay? And you realize that between the strong repulsion and the attraction that we will calculate, there must be some minimum in the middle. And this is indeed the equilibrium distance of the molecule, okay? The molecule has a certain binding at a certain equilibrium distance of a few angstroms, okay? In principle, you might try to calculate everything here and try to see, for instance, what would be the vibration frequency of this molecule. This is an experimentally measurable and meaningful quantity, but to calculate this, you need also this piece of the thing. We'll just concentrate on this, okay? So we'll not be able to address the binding, but the tail at large distances, yes. Okay? This is called van der Waals attraction. The exercise we'll do it on hydrogen, but we might do on any other neutral atom with another neutral atom. Okay? The effect is pretty similar. So this will be our first exercise, indeed, where we go out of the world of one electron. Indeed, here we have 2 electrons at least. Although we'll make a very small excursion. Okay? So for the time being, just accept this as an article of faith. We'll justify some of the things that I will use by doing Pauli principle and things like this towards the end of the course. Okay? So for this time, you will have to believe me on something, okay, which you will learn in a while. Okay. Now, the Hamiltonian would be what? Well, it's simply the Hamiltonian of the first atom, which is the momentum of the first nucleus squared divided by the mass of the nucleus, plus the momentum of the first electron. I write this as big P and this as small p over twice the mass of the electron, minus E squared over R1, okay? Plus the momentum of the second nucleus divided by twice the mass, plus the momentum of the second electron divided by twice the electron mass, minus E squared over R2. You realize that I'm measuring here. Let me draw this thing better here. I'm measuring here R1 from the first nucleus, okay? And similarly here, I'm measuring R2 from, well, let me just draw it differently here, from the second nucleus, okay? So if I really had to fix a common origin, for instance here, there would be big R1, which is the coordinate of the first nucleus, and then the coordinate of the electron would be big R1 plus small r1, okay? Then there would be big R2, the coordinate of the second nucleus, and then big R2 plus small r2, the coordinate of the second electron, okay? This all refer to a common origin. All right, but certainly I can write the interaction potential in terms of the relative coordinate with respect to the center, right? This misses several contributions. Let's see how many. Well, here every electron interacts with its own nucleus, okay? But in practice, in actual fact, there is an electron that feels the other electron, okay? There is a nucleus that feels the other nucleus. And there is even more. There is this electron that feels the other nucleus, and this electron that feels the first nucleus, okay? So there are 4 terms that are missing here. And they are all Coulomb terms. So let's write them. E squared over R2 minus R1, okay? The 2 nucleus feeling each other, repulsive. Plus E squared divided by R2 plus small r2 minus R1 plus small r1. What is this? It's the 2 electrons repelling each other. Again, plus. Now there are 2 attractions. This electron attracts the other nucleus. So for instance, there is minus E squared. The electron is at R2 plus R2, and the other nucleus is at R1, and this is the energy. And then there is the final contribution that is just the first electron, which is here, attracts the second nucleus. I better write it like this. R2 minus R1 plus R1. Okay? Is this clear? It's kind of big, huh? Okay, this will be somehow my unperturbed Hamiltonian for atom 1. This would be my unperturbed Hamiltonian for atom 2. And the sum of these 2 will be my H0 in some sense, the unperturbed Hamiltonian, 2 atoms so far away that no interaction counts. All right? So you know everything about this problem, because these are 2 separated hydrogen atoms, okay? So you know the spectrum of this, the spectrum of the other. For instance, can I ask you at this level, okay, what is the ground state energy of this problem? Huh? The ground state of H1 is how much? minus a Rydberg, okay? The ground state of this is minus a Rydberg. So to this level, the ground state of the combination of the two is minus 2 Rydbergs, okay? So you conclude immediately that this 0 here that I was considering before is minus 2 Rydberg, okay? This is the unperturbed energy of the two atoms very far away. All right? Good. Very good. And you know the energy eigenstates, they are just the usual atomic states for 1, for 2, and so on and so forth. Now, we want to really consider this object, which is our candidate perturbation. All right? This is our V, or lambda V, whatever you want to call it. There's no need for lambda, in fact, now, because, I mean, I know how to write the second order formula without any further lambda. Now, let's see. R2 minus R1 is exactly what I was calling R before, okay? So you see, it's the position of atom of nucleus 2 minus the position of nucleus 1, R. All right? So this is R. It's big. Here I have R2 minus R1. So let's see, this denominator is, this is E squared over R plus R2 minus R1. You see? This is E squared over R plus R2. And this is E squared over R minus R1. Okay? So these are the 4 terms that I have. They have a big object, R, which is large, and then other objects that are kind of small, because these are of the order of the Ball radius type. Remember, R2 and R1 are coordinates with respect to the nucleus. So they are, I mean, the atomic orbitals are on the scale of the Ball radius. So these are small numbers, while this R could be very large, okay? So obviously here I have 4 terms, 2 with positive and 2 with negative, but there are strong cancellations, because, I mean, after all, if I had 0 here, they would cancel exactly. So I need to extract this cancellation in a neat way, all right? How do we do it? Probably I will stop just immediately after having expanded this. You will see that the result of this is very intuitive, okay? It's dipole-dipole interactions, okay? But since maybe electromagnetism is a little bit far away, let's do it, okay? After all, this is a neutral object and another neutral object, okay? And the first non-negligible contribution is dipole-dipole type of interactions. Okay, so the trick is the following. In all these 4 things, you do have an object like 1 over R plus D, where D is a vector, which is much smaller than R, okay? You see here D is R2 minus R1, here D is R2, here is minus R1. So let us consider this object in general. How do I expand this? Well, it's simple, right? Because this is 1 over the square root. The norm of this vector is what? R squared plus D squared plus 2R dot D. All right? I'll do the steps one by one so that you follow me. Now, R is large, okay? So let me bring it out. 1 over R. And then I have the square root of 1 plus, let me write it as D squared over R squared. And the other term is 2R dot D over R squared. All right? Now, if I have a term like this, I can expand now, because these are, after all, small things, 1 plus small things. So I can expand the square root, but it's a square root in the denominator. So I urge you to verify, okay, with all your Taylor expansion tools, that if I have 1 plus a small quantity to the power minus 1/2, so in the denominator, this is equal to 1 minus 1/2 x. That's simple, okay? Perhaps, I mean, you don't always recall by heart, and therefore you have to calculate that there is also a second order that is this, okay? This second order is useful, okay? So don't think that you can get away with just the first order formula, okay? For a reason that will be clear in a while, okay? So I apply this expansion to this object here to obtain something like this. So this is roughly equal to 1 over r times 1 minus 1/2 this object, you see? So d squared plus 2r dot d divided by r squared plus 3/8. In principle, I have the square of this. But look carefully. This is, the first term is 1 over r squared. The second term is 1 over r, okay? So the second term is really the big one. The other is quite smallish, okay? So really, I can just keep the 2r dot d over r squared and square that only, okay? There would be other things, but these are smaller than this. Now, a small lecture about what to keep and what not to keep. You have to keep, first of all, consistently in the small parameter that you want, all terms of a certain order, okay? So for instance, in the first term, there is a term that is r divided by r squared, so 1 over r. So don't think that, well, 1 over r and 1 over r squared. It's because of this 1 over r squared here that you cannot avoid keeping another 1 over r squared that comes now from the second order of this. This is 1 over r. If you square, it's 1 over r squared, same order as that. Okay? So whenever this happens, that you have two different orders, always keep also the next one such that it is of the same order as what you have kept. All right? Never put this without that. Okay? You might say, okay, I don't keep that, and I don't keep this as well. But then it's too dangerous, too risky. Okay? It might be that everything then cancels, and then you need some terms. Okay? So whenever you expand, always be generous and expand a little bit more than what is the minimum necessary, because maybe it will be useful. Okay? If it is not useful, you are always ready to drop it. Okay? Okay. So that's what we did. We expanded to second order in order to keep the minimum, which is this and that are of the same order, 1 over r squared. Okay. Now I have this, and I can apply to this. Well, this is in fact simple. There is no correction, so nothing, just 1 over r. Then I have this, then I have that, and then I have that. And there are different signs, okay? So let's see. Should I do it? It's a careful algebra that must be done. So for instance, in this case, you have d equal to r2 minus r1. Okay, let's try to do it, at least to see the effect. Okay, so here I would have e squared over r, no problem. Here I would get plus e squared over r, okay, times 1 minus. D is really r2 minus r1. So r2 minus r1 square plus 2r r2 minus r1 divided by r squared. There is a factor 1/2. And then there is a factor plus 3/8. And then there is a 2r r2 minus r1 squared divided by, sorry, r2 minus r1 divided by r squared, like that, okay? Now you have another term, okay, similar, so with a minus in front, however, e squared over r. Let me write it up. So it is similar to that. So 1 minus 1/2. You have R2 square only, because you have R2 and not R2 minus R1, plus 2R R2 over R square, plus 3/8 2R dot R2 over R square square. Okay? And finally, similar, minus C square over R. But now you have 1 minus the square of R1. Then you have, careful, you have minus R1 this time in place of D. So the second term here has now minus 2R R1 over R square. And then here the sign is not important because there is a square. So you have 2R R1 over R square square. Okay? These are all terms up to that order. And now you see the charges cancel because you have 1 plus 1 minus 1 minus 1. So the 1 over R is not there. You expect this is charge. There's no net charge. So this, and this goes. Now, let us see here. From this term, for instance, you will get, okay, let us first look at this. Okay? Here you have R times R2 minus R1. Okay? Here I have R times R2. And here I have minus R times R1. If you check, there are minus signs such that this object cancels exactly with this and with that. Okay? Check. Now, this means that if I am too lazy and I say, okay, let me keep only this term and not d over r squared and the other term like 1 over r squared, just this, okay, I would end up with the 0, no effect, and therefore excessive laziness is punished. Okay? So I have to keep this other term. But if I keep this other term, I should not forget the square, which is of the same order. Okay? So I'm forced to do that. And now I have to keep track of all those squares. You see there are lots of squares. R square comes from here. There is an R square there. R1 square is there. R1 square is there. Now, those squares cancels, okay? Because R square with the minus sign here, and there is a minus and a minus, a plus there, okay? So the square from here cancels with the squares appearing there. Nice. But the R2, R1, the cross product remains, okay? And this term, well, this term also has to be massaged, okay? So please, can I ask you to just do this little final algebra? It takes very, very little, but if I keep doing plus and minus, essentially I've exhausted the time. So the result is the following. I first write it and then we comment. E squared over, let's see, the R appears in front, but also there is a 1 over R square there. So it's 1 over R cubed. Okay? Then I have R1 dot R2. This comes exactly from this mixed term. Okay? You see there is a factor 2 and the minus sign that cancels this 1 over 2 and the minus, and you get just R1, R2. The R square is already there. All right? So that is there. Minus terms coming from this. Okay? So you can easily see that these are essentially 3. Yeah. Where? Because it's a mistake. I forgot it. Simple explanation. Okay? Good. So you just take this thing, the 4 and the 8 here gives me simply 3/2, and if you just do the algebra correctly, by the way, this really is r divided by r makes the r hat, the versor r, okay? You see? And then there is another 1 over r that's squared, ends up there, okay? So that term is simply minus 3 times r dot r1 r dot r2, okay? This is what you get. Okay, let's try to fully convince ourselves. You see here there is, again, a square term, r square. This r square is not important. It cancels with that. The r1 square is also not important. It cancels with that. But all it survives is now the minus 2 r2 r1 from this object, okay? So if you do the whole calculation, you will realize that this is what you get, okay? There is a minus, the 2 and this and the other square and other things will just conspire to give you a minus 3. All right? So this is the result. Well, it's very late. Let us look at it. You have probably seen it before. This is exactly the interaction between two dipoles. The first dipole is E times R1, okay, is this dipole. The second dipole is E times R2, okay? They are connected by a certain distance r, okay? And you know that the two dipoles interact with 1 over r cubed, but they have a orientation-dependent contribution, okay? So there is a term that is just the scalar product of the two dipoles, but there is a term that tells us how the two dipoles are oriented with respect to the joining line, okay? In particular, this term is there because the two dipoles, if you put them up and they are joined like that, obviously they would like to stay like this. But this configuration is different from this or this configuration, for instance, okay? So the energy is different. This and this, okay? Because of, if you calculate where the charges are and the distance are, you see which are the best configuration for the dipoles, okay? And the best configuration is given by this thing. So you want to, for instance, try to use the most you can out of this. So you see, if I have a certain r, I can make r1, okay, r2. So if the two objects are like this and like this, okay, then, obviously like this, okay? So if the two dipoles are oriented like this, so this is a positive contribution, okay? And this is, and this is a positive contribution, but this is minus 3 times that, so you get minus 2, okay? So you can calculate the total contribution. You get plus 1 from here, and minus 3 times from there, so minus 2. And this is better than putting them, for instance, orthogonal and opposite, because orthogonal and opposite will give you just minus 1, okay? This quantity is, say, fixed, or say a certain amount, okay? Say the ball radius or whatever, okay? So try to have a fixed length dipole, and try to minimize that energy, you will realize that the best you can do is not this, but this, okay? This is minus the square of the dipoles, and this is minus 2 times, all right? Okay. In any case, this is the contribution, and now you can write this as, if you want, also in terms of x1, x2, y1, y2, z1, z2. So suppose that r is in the direction z, then you immediately see that this is x1, x2 plus y1, y2. There is a plus z1, z2, which is cancelled by minus 3, and you get minus 2 z1, z2. Okay? So this is the dipole-dipole term, which is a perturbation of the two hydrogen atoms. Okay? Now, next time we will finish this calculation, but we will not say goodbye before we understand at least the main result now. You realize that this is a perturbation, okay, that is odd for every individual x, for instance. x1 is odd. x2 is also odd. So when I put this thing between the same state of the hydrogen atoms, each one of this term will give me 0. Okay? So on average, this result will be 0. So the first order correction is actually 0. You understand why? Because the wave function will be essentially a wave function of this times that, okay? Then you put this in the middle, this operator, okay? The wave function appears to the right and to the left, but the operator in the middle is odd, and therefore the result is 0. So no first order correction. However, to second order, we will have corrections, but to second order means 1 over r to the 6, which is exactly what we were expecting, okay? Minus a constant divided by r to the 6. The constant will have to be calculated by summing all the important matrix elements. But the 1 over r to the 6 is obvious. It's second order perturbation theory. And even the minus sign is obvious. The ground state always decreases its energy when you account for second order perturbation. Okay? So the sign and the order are just obvious from second order perturbation theory. The detail is only how much is C, which we'll do it next time. All right? Okay, so if there are no questions, yeah. Repeat the question.
Okay. The first particle. I said about the direction. I'm talking about the direction distance. If the both were not in the same direction here.
They were not in the same direction?
Yeah, direction. Okay. Yeah. If
They are not in the same direction. They could be in any direction, okay? For any direction, you calculate the interaction like that. Now, what I'm telling you is that the best directions to minimize this energy, classically, I'm talking about classically. I mean, what they do quantum mechanically is more complicated. But if you had just classical vectors of a fixed length, and you ask what are the best possible energies for those two dipoles, okay? Then there are two possible competing things. This, okay, because this is very happy, but this is not particularly happy because R and R1, R2 are orthogonal. Or this. In this situation, this is a little bit unhappy, but this is very, very happy. Okay? So in the end, this wins over this. All right? That's it. This is classical, however, just to remind you of dipole-dipole interactions. Okay? Yeah.
As for the aperture of the Hamiltonian at 0, that's not.
What?
For H0 zero. It's the momentum of the equation.
Mm-hmm.
So if we are not in the center of mass frame,
Mm-hmm.
dig P should be zero.
Well, to be honest, the center of mass thing, it's in some sense one might want to ignore the center of mass. But I agree with you that if you fix the center of mass, the momentum of the center of mass will be undetermined by Heisenberg uncertainty. So in some sense, there is a little bit, you have to imagine kind of wave packet of the center of mass, which is not moving in some sense. Okay? So in some sense, the center of mass really contributes no kinetic energy, doesn't move. They are there. Okay? So the question about reference frame is a bit fishy, but not so much in the end. I mean, in any reasonable physical setting, these two atoms are just sitting somewhere, and you want to know what they feel, how do they attract, okay? So what we will see next time is how to describe the wave functions of this thing. It's two of them, okay? So we will learn how to write the wave function of the composite objects, okay? And then how they, I mean, the perturbation will distort those wave functions and the attraction is born, okay?
So,
Forget about center of mass, in other words.
so this looks like all this is just for an instant, a given instant. Because we have contribution from electrons, but we know that electrons are moving around.
No, we will calculate quantities that do not depend on the actual position of the electron, but only on averages with wave functions, okay? So the results that we will calculate are valid. I mean, obviously the atoms, the electrons move, okay? And they are valid if the atoms stay fixed there, okay, while the electrons run by, the results are valid. Obviously, if let the atoms move, then R changes, and you should ask what happens to, this is another problem, okay? But if the atoms are fixed, the electrons move, we will calculate the result. In quantum mechanics, it's not that this is a quantity that depends on time and changes. This is a quantity that needs to be averaged on some wave functions, which we'll do next time. The electrons move, but we know how to account for that in quantum mechanics, all right? Not with the classical motion. Forget about classical orbits, okay? But with the quantum average, expectation values. That's all we have done until now. 20 lectures, okay? Not motions of orbits of planets, but wave functions, okay? I must warn you, this is quantum mechanics class, not celestial mechanics, okay? Okay, good. So see you tomorrow.